All right, let's get us started. We were discussing regression, and we ended up, we defined rich regression and logistic regression, two famous models that are very useful for much of what we're going to do in the next several weeks. So very basic but very important algorithms to keep in mind. Now remember that the most important point, or one of the important points rather, that we saw in regression is the selection of the loss function, right? And especially, that is especially true when you regularize the regressor, right? Because it makes sense in general to include to use the two or the square loss for the regressor itself. But when you're considering regularizing it, the question is, how do you want to regularize it? And here it depends on what you want to model and what you want to extract from that information, right? So remember, that's pretty much similar to using PCA versus ICA versus factor analysis, right? It all depends what we want to extract from that information that we have, meaning the data samples that I'm given, right? So depending on what you want to extract, depending on which assumptions you want to make, then you're going to use a loss function or another. And remember that we talked a lot about this early on in the course, like probably first lecture, that everything in science, and machine learning obviously is not an exception, everything in science depends on its assumptions, right? And here's where your assumptions count. Where are the assumptions that I'm going to consider that are going to define my my loss function. Now, again, it can also be because of the information that I want to extract from that regressor, right? So if I want to extract information that defines the correlations or the least squares loss, then I'm going to use a square loss, right? But if I want to consider an algorithm that extracts, say, a sparse representation, right? Then I'm going to use either the one loss or the, there's one that people call the zero loss. That's not a loss. I mean, it's not a metric. It is a loss, but it's not a metric, right? Because it's zero. But there is a special definition for that. There are specific losses that you could derive yourself, right? And that is the point, that you can derive whatever loss that you need to, right? You don't have to stick by the ones that we have given here on the board. You can derive your own loss, the one that works for you, right? That does what you expect the regressor to do, right? So if you're a self-driving car and you want to move on the road using a specific constraints, then you have to add those constraints in your loss function, right? There's no other way that the car is going to know what it needs to do if it's not implemented in the loss. There's no magic in machine learning, right? Everything is given by the data that you give it to the system and the loss function, right? And remember, by itself, data is dumb, right? Data doesn't know anything. Data doesn't have any meaning. The important thing is that you select the data that represents what you want to learn, right? So there is right now, this very moment, there's a very important topic that is growing in relevance in machine learning, which is biases. And basically, put it another way, bias, it's a way to say racist, right? Or sexist, or any other ist that you want to consider. And why is that? So let me give you, for example, a couple examples, right? Many face recognition systems have problems with black faces or darker skin color faces. And a big company was trying to create a chatbot that would learn from data, and then some people, to play a prank on that company, they started sending, because in order to learn, it had to interact with people, right? and people just connected it and interacted, and some people did a prank on that company, and they gave that chatbot so much racist and xenophobia information that the bot became a Nazi, right? And that is very problematic. Someone has to choose the data, right? But if you select the wrong data set, then that's what the algorithm is going to learn, right? And I have had friends telling me, oh, but the algorithm by itself, the machine learning is not racist by itself because it's just a machine learning. Of course it is. That's the definition of racism, right? Or xenophobia or whatever it is. Of course it is. The problem is how are you going to derive methods that are not. And again, it can be given because of the data, as I just described here, but it can also be given by the loss function. If you have the incorrect loss, that's what the algorithm is going to learn. The algorithm is only going to minimize or maximize the criterion, the objective function that we define, right? And if our objective function is to be a racist, then that's what the algorithm will learn. And if you're a self-driving car and the loss function doesn't account for certain things that the self-driving car has to account for, then there's going to be an accident, right? And you have to account for all these things. So at every point in time, you have to address the constraints given to you by the problem. Another way to address this is by having multiple objective functions. And then if you have multiple objective functions, this is called multi-objective optimization. So let's talk about this briefly. Okay. This is nothing truly new, multi-objective optimization. In fact, we have already talked about multi-objective optimization, haven't we? So, for example, just in our last lecture, when we were defining regression, we had two criteria, right, for regularized regression, right? We had the regression criterion and the regularizer, right? So for example, again, in regression, we had two criteria, ED and EW, right? That we want to minimize. And then we said, we don't know what to do, so I'm going to add this on this other, and I'm going to add a parameter here to control the relevance of each one, right? Now, two problems with this, or all right, 2 points with this. The first point is not a problem. The first point is, well, in regression, it did make sense to combine these two, right? Because I want this to constrain this within the same criterion, right? This is a way to first make this, as was mentioned by you guys, to make this invertible, right? In our least square solution. But okay, that can be easily solved with PCA or eliminate the null space. But also to determine which type of outcome I want to obtain, right? Do I want to get the least square solution? Do I want to get the regularized least squares? Do I want to get the weighted least squares? All the things that we saw, right? So these things are very important. And this is obviously going to change the result. We also saw, so this is for regression, but we also saw this in classification, didn't we? For example, in discriminant analysis, when we talked about discriminant analysis, we said discriminant analysis maximizes this criterion, V transpose MAV over V transpose MBV. Right? Again, this is the same as maximizing the criterion MB inverse MA, right? So again, combining these two metrics here, right, into a single criterion. Okay, it's one way to solve the problem, right? And there's nothing fundamentally wrong with this, just one way to do it. but it's not always appropriate, right? In many instances, we want to simultaneously maximize or minimize several criteria. So we can define this more formally if we have k functions that we want to simultaneously minimize or maximize, let's say minimize, then I can write this as minimize the parameters of u1 theta, and this could be theta of the parameters or theta 1, where theta is theta 1, theta 2, theta, and so on, right? And each theta I would be a vector of all the parameters that are included in all the functions. So I want to minimize u1 theta, but simultaneously I want to minimize u2 as well, and up to my k different functions criteria that I have, right? And subject to, right, I need to constrain this, as always, to my parameters being in some domain, okay, some space S. Now, in general, we're going to say or assume that these ui's that I have here, right, are mapping functions that go from our p-dimensional feature space that we begin with to R, right? They provide a value, a criterion, right, that measures the objective function. And then obviously this S in general is going to be in my space, my feature space, define my feature space, right, as well. All right, so in order to see how we can solve this, let's start with a couple definitions. A decision vector, theta 1, let's say, is said to dominate theta 2, which is another decision vector, right? Another possible solution. If ui of theta 1 is smaller or equal than ui of theta 2 for all values of I from 1 through k. And uj theta 1 is smaller than uj of theta 2 for at least one index j. Okay? So that means that we would generally prefer theta 1 as the outcome of my parameters that I need to estimate for my problem, my regressor, let's say, parameters of my regressor. We prefer the parameters theta 1 if ui, remember each ui, it's one of our criteria, right? So ui of theta 1 has to be smaller or equal than every other ui of theta 2, right? So it has to be at least equal, if not better, than theta 2, right, for every case. But at least it has to be better in one case, because otherwise, if it's not even better, then they're equal, right? Okay, in that case, we're going to say that theta 1 dominates theta 2, okay? All right, second definition. a decision vector. Now let's call it theta star to represent our minima as usual. Theta star, and theta star obviously has to be in my space of allowable parameters, right? S is called Pareto optimal if there does not exist another decision vector theta in my space S for which ui of theta is smaller or equal than ui of theta star for all k, and uj of theta is smaller, strictly smaller than uj of theta star for at least 1j. One value of k. Okay. So a decision vector, we're going to call it Pareto optimal if basically it's not dominated by any other vector. Okay? So let me write this as another possible way to state the same thing. A Pareto optimal solution is not dominated by any other solution vector, or let's just say any vector easier, and any other vector. So our goal now is to find that Pareto optimal solution, right? Now, I want to be clear that what I stated here before, that theta 1 dominates theta 2 if they're equal for at least everything, if not better, but at least better in one of them, right? But in general, you could have multiple solutions for which they're identical for all the ui's, right? So ui of theta 1 is always equal to ui of theta 2. If that happens, then these different thetas that define all the Pareto optimal solutions define in your space S a function that is called the Pareto frontier. Okay? That means that all these possible different functions, solutions in that function, right, are equally good. There's no, given your criteria, there's no way to determine which is better. Just they're all equally good. Okay? And your goal is to find at least one of them. Right? That's the goal. So let's see a first algorithm to find this. It's called the Epsilon constraint algorithm. So the way the Epsilon constraint algorithm defines this is by including all the functions, all the objective functions uj's or ui's in the subject to constraint here for the optimization. Okay, so first I'm going to set some function. Let's call it ul. Okay, this doesn't work. I'm going to use the first function. Let's call it ul. Okay, and I want to find the parameters of that ul that minimize my criterion. Okay, so far so good. And now I want to find the parameter, so the argument. Now this, I'll say that is subject to the fact that uj of my parameters has to be smaller or equal than some epsilon value of j for every value of j that is different than L. Okay? Now, obviously, this is also subject to the parameters being in my space S. And here, where L is going to take the values 1 through k, right? All the possible set of values. Now, this, if you want to work with this, this is a fantastic way to solve multi-objective optimization. Easy to implement as an optimization algorithm, but the problem is you don't know what the epsilon j's are, right? So you could try a few parameters. This has to be a small number, but you just don't know how small, right? So if you're lucky enough to find them, then that will work well. But if not, then this just doesn't really work. So can we find another solution? Okay, let me do a drawing of why this may not work. So imagine that my feature space is, or my parameter space is two-dimensional, like this. And I have, or let's call this rather, okay, so let me do this. Why don't I do, this is, I'm going to draw here the different criteria that I have. So this is a criteria space. So let's say that this first dimension is my ul that I want to define here. And this, the other uj's, right, are going to be orthogonal or drawn orthogonal to this. And now I'm going to draw a function of solution, say maybe this one, right? And now let's say that my solution, I'm looking for my solution here of ul, right? I want to maximize this. Now what I do know is that uj has to be smaller or equal than some parameter. So I can write this as maybe here, right? And oops, I did that the other way around, didn't I? Why don't I change this? Sorry, guys. It's easier to erase this. So j and L, like this. So now the question is, let's assume that my Pareto frontier is, say, I don't know, maybe this one right here, okay? From this point to that point. That's the Pareto frontier for sake of discussion. And now if I select an epsilon that is smaller than this, right? so epsilon is right here, then I'm looking in that region of the space, and I'm going to be able to find the solution, right? You see that? But if my epsilon were to be here, then I will also find the solution, right? And that's not in the Pareto frontier, that's not Pareto optimal. See how this works? And the opposite could happen, right? The Pareto frontier could be here, in which case then I want this epsilon here and so on, right? So it's always it's always problematic. So what we're going to do instead is define other solutions. One way to solve this problem is to find the argument that minimizes the following. UL, I'm going to keep it the same as before, but now I'm going to add an additional constraint here of some functions hj times a scalar. Here let's call a scalar s. Okay. Subject to, as before, that uj of theta be equal now to this hj of epsilon j for every j different than L, and subject to this hj have to be between 0 and some scalar s, and the parameters in my space, capital S, this is small s, that's capital, and this has to be still again only for j different than L. And now when I simultaneously optimize for this, what happens is that I am adding an extra parameter to optimize that allows me to find an equality here that simplifies the optimization problem, or allows me to actually compute the optimization. This algorithm has been shown to yield the correct solution, the Pareto optimal solution. Now, another way that you're going to see all this explained in the literature is by Nash equilibrium. And obviously there are small differences, there are reasons for this, but for what we are concerned, which is going to call them the same thing, or about the same thing, okay? As far as we are concerned, they are one and the same. Now I have uploaded, as always, in Canvas a paper that explains all the derivations of this method and how this method is used in ridge regression. Okay, so you have that there in case you want to follow up on the lectures. All right, another thing that I would like to mention briefly, because this will come back to us. So this is very useful for regression, this method, and maybe for discrete analysis and things of that nature. But another method that we'll be using in deep networks, deep learning, is the Minimax optimization. So very briefly, let's introduce this now, and then we will come back to it when we talk about deep networks. So for this, let us assume, or let us simplify the problem. So let's assume that we have a very simple case of a discrete game. Okay, a game, just we're playing a game, a real game, and it's a discrete game, right? Not a continuous, a discrete game. We're also going to assume we have two players in that game, player 1, player 2. Okay, and we're going to specifically derive the optimization for a type of two-player game that is called a two-player zero-sum discrete game. Basically, a zero-sum game means, this one here, means that if player I, right, gains, I know, X, right, then player not I is usually written as negative I, just means whoever is not I, right, must lose X. Right? So that there cannot be any gains or losses in the game. The game is zero sum, right? When you sum the benefits for one player plus the benefits of the other, they are constant. You cannot add benefits, you cannot subtract benefits, right, from all the players. That makes it very easy to derive the algorithms. Now, a two-player zero-sum discrete game is given by a what's called a payoff matrix with entries. So this is given by a payoff matrix with entries. Let's call it P, capital P, the payoff matrix, and the entries of the K and L row and column, right? What this payoff matrix defines is the payoff, right, the benefit for each of the players, right? So what we're going to say is player I, or let's call it player 1 for simplicity. Player 1 selects K, right, here. And player 2 selects, what do you say, L. Come. The goal of player 1 is to select the K that minimizes the objective function. And the player 2 selects L that maximizes this objective, okay? I'm also going to add here to this two-player zero-sum discrete game the constraint that each player can only select one outcome, right, or one action, one solution, right? No multiple solutions. This is a very classical constraint in the problems that we have. It's called, I think it's called purist strategy, right, I believe. All right. Now, let's assume that we are player 1 for a second, okay? I'm player 1. Remember, I'm player 1, therefore I want to find a K that minimizes the objective, yes? But wait a minute. I know that player 2 wants to maximize the same objective, right? So I know what player choosing is going to be. I don't have to wait for player 2 to perform that action. I know what it is. It's going to be the one that maximizes the objective function. I have access to the objective function, right? So what player 1 is going to do is going to select. So player 1 is going to select the minimum, not this one, is going to select the minimum of the maximum of PKL, right? Maximizing L, minimizing K, right? So I not only want to minimize my result, I want to find the minimum given the fact that I know player 2 is going to select L, which maximizes my objective, right? Now, what does player 2 want? Well, player 2 wants to maximize, but player 2 knows what player 1 is going to do, doesn't he? And therefore, it knows that player 1 is going to try to minimize, find a K that minimizes my criterion. So it's going to try to find the maximum L given the minimum, right? And that is the same as looking at rows or columns in that matrix, isn't it? Because you find the row or column that minimizes or maximizes the criteria or the criterion of the players, and then you just from that row or column you select your minimum or your maximum depending whether you're player 1 or player 2, right? Now this is all very nice, but in general the max L of the mean K of PKL is either smaller or equal than the mean of the max. Oops. The equality in this equation, this last equation, the equality holds precisely when the game has a Nash equilibrium or a Pareto optimal solution. So the equality holds when the game has a Nash equilibrium. Okay. Now, also for feasible bilinear problems, the equation above holds, and remember the bilinear problem takes the following form: the minimum of the maximum of X transpose PX, where I'm going to select, say, X and Y. I'm sorry, PX, PY. Okay. Subject to that AX is smaller or equal than B, CY is smaller or equal than D, Now remember, this is this one here is the expected payoff function or matrix, right? Which we can define, if you prefer, as the sum. This is the product, right? So it's going to be the sum of ui vj pij for all ij's, right? Same thing. And our constraints that I have added here, right? So these are constants, scalars that I have, and these matrices determine, right, the metric. If it's a symmetric positive semi-definite, it'll define a metric that determines the type of constraint that I want to add here. Okay. And that it can be implemented as a bilinear optimization problem, right? You go into MATLAB or whatever your favorite software to implement these things is, and you just use the bilinear formulation to solve for a problem. Okay. Now, this last result, in case you want to learn more about this, I did not post this in Carmen, but if you want to know more, you just need to Google it. This follows from a famous theorem, which is von Neumann's Minimax theorem. I assume that this is covered in optimization theory in one of the courses in optimization that we teach. I would have to assume. Again, optimization goes beyond what this course can cover, but remember, it's important to know the very basics, at least, of optimization, so that you know that there are these different types of optimization functions and algorithms that you can use to just plug it into the system, right? As far as we're concerned, we define the objective functions. We have to know which type of optimization this is, right? Have to know the format, and then just ask our colleagues in optimization, okay, which is the best way to implement, or which is the best algorithm to use for this. Okay, any questions? Yes, question there.
The conclusion of the theorem, is it that the Nash always exists?
No, if it exists, right? The Nash equilibrium may not exist, right? You could end up with a criterion, right, that doesn't have an equilibrium for a minimax problem, or for multi-objective in general, right? For multi-objective optimization, you may end up with criteria that are inconsistent with one another. There's nothing you can do. There's no Pareto optimal solution, right? And then there's nothing, absolutely nothing that you can do on that. Right? Now, Nash equilibrium in the most basic term, and in the discrete case, most basic term is very simple and very clear to understand, right? So the classical example that economists like to talk about is a prisoner's dilemma problem, where you and a colleague have robbed a bank, and then you're caught by the police, and they put you in separate rooms, and you have to decide whether you play guilty and tell the court that your colleague also robbed the bank with you, or you stay silent, right? And then you have a table, right? The payoff function table, or matrix, that tells you how many years you're going to spend in prison if certain things happen, right? So if you and your colleague do not say anything, then you go free, for example, right? If you say that you're guilty and you implicate your friend, then you spend a year and your friend spends, 5 years, right? And if your friend your friend recants on you, then you spend 5 years and he spends 1 year, right? And if both recant, then you spend 5 years, both of you, right? Or 3 years, whatever it is. So things of that nature. And then you have to find, okay, what is my equilibrium, right? What is the best outcome? And if I have to assume what is the best outcome given the worst possible outcome of the other player, right? Then you have to determine here whether it pays off or not. And depending on the values on the payoff matrix, it does or it doesn't, right? I mean, and depending on you as well, obviously. There's another question. Pareto optimal? No. No. In general, it's not. In general, there's a Pareto frontier that I mentioned, which is defined by all the parameters, all the set of parameters that are equal, that for which this equality holds. And that does not hold. Right? So it's equal everywhere, and it's never better. That's the general case. And your goal is to find one solution, right? Just one. Because they're all equally good. According to your criteria, they're all equally good. There's none that is better than the other. Doesn't mean that that's the ideal solution you want, right? But if that's not the ideal solution you want, it's because you're missing another criterion that you need to add to differentiate it among those that you do find. Any other questions? Nope. All right. Let's move on then. Now that we have covered a lot of ground, right? I think that we really have a lot of knowledge, hopefully, by now. And please keep reading all the things that I post in Canvas. If you need to rewatch the lectures, whatever it takes. But we've covered almost all the fundamentals that there are to cover in machine learning, right? There are always topics that we don't have time to cover, obviously. But we've covered a lot of ground on many things. So I want to spend a few minutes today describing a method for manifold learning that is really useful, it's a fantastic algorithm, many applications, and it's going to require that we use all or several of the concepts that we have defined over the last several weeks, okay? Now, this method that I'm going to introduce today, I want to talk about this one specifically because it was derived by Misha Belkin, who is a professor here at Ohio State, right? It's a famous method. Okay, so let's see this. But before we get to the actual algorithm, I want to talk about manifold learning in general. And for this, I want to go back to PCA. And PCA, of course, it's the most basic manifold learning that I can derive using linear least squares. But it's a linear manifold, meaning it's a subspace, right? So let's see what that means. Okay. So let's go back to PCA for a second, shall we? So imagine that your feature space is the real domain of 3 dimensions, okay? And in general, RP, obviously. And then what we have, it's a number of observations, right? These are our simple feature vectors. These are our simple, as always, feature vectors, xi's, right? Our xi vectors. And then what does PCA do? Remember, PCA computes the mean and covariance matrix, and then from that it finds the hyperplane, right, that best approximates all the samples, right, optimally approximates all the samples with respect to the least squares criterion, right? And it will find this hyperplane or subspace, right? Subspace, nothing else than a linear manifold or a hyperplane, right? Within my original feature space, right? So if I star in the general case, if I star in Rp of p dimensions, then I'm going to end up with Rq of q dimensions, where q is much smaller generally, right, speaking, than p. Certainly smaller, but generally even much smaller. Okay. So what I wanted to next is to do something that we have done in regression, right? Because in regression, know that what we were doing is, let's go back to regression for a second. This is regression. In regression, we might have had samples like this, right? In which case we said, oh, we're going to find the regression, the function that regresses these points in the least squares sense. In the least square sense means that we were going to use the loss function, right? The loss function that we were going to use was the square loss, right? That's what it meant. And then in that case, we find this line, right? This is our most basic. But then we said, well, but we can change the functions that define my space, right? Instead of the original basis vectors that I have, EI, EJ for my basis vectors, right? So EIs are my basis vectors. I'm going to change these for phi i's, right? Where these are my functional basis, right? Basis functions. And so now I substitute this by this. And what does this do? What does this is that now this dimension here, right, this feature is no longer representing a linear representation of my first feature in the original space, but a linear transformation of that feature, right? And that basically allows me to now address the problem having fiducial points, sample feature points like this, and find a solution that looks maybe something like this. That compare to the least square solution, which would have been maybe in that case would be something like this, right? Okay, in the original space. Using the original basis functions, basis vectors. Okay. So that's what I want to apply here in this case, right? So I have again this three-dimensional space. I have my simple feature vectors here, right? Just the points. So I have my simple feature vectors here. And maybe they look something like this, right? And now what do I want? I want, instead of finding a hyperplane, I want to find the manifold, right? Maybe it looks something like this. The manifold here that defines my simple vectors, right? You see that? So that's an extension, a nonlinear extension of this, right? Of this method. So this is linear, and this is nonlinear. This is PCA. Oops. And this is manifold learning. And the question is, how are we going to learn this? And this is a very difficult question, right? Because obviously we know how to learn linear subspaces with linear least squares, right? But once we start including nonlinear functions, that becomes really tricky, remember? So let's see an algorithm to do just that. So we're going to start with, well, we're just only going to see one method because we don't have time for more. But the method is called Laplacian eigenmaps or Laplacian maps. And the name will become clear in just a second, why we call it that, where Misha decided to call it that. Okay, so as always, let's start with our simple feature vectors, right? So let's say I have x1 through xn, and that they are defined in a feature space of p dimensions. And our goal, so these are our xi's here that I have, right? And these xi's are obviously in Rp. And our goal is to find a representation. Let's call this representation yi's, where my yi's are in q dimensions, right? So here it'd be in the PCA space of q dimensions. Here's a manifold of q dimensions, okay? So I'm going to say y1 through yn in Rq. Now, again, as always, q smaller and generally much smaller than p, right? So think about an example. Remember, you actually did this in one of the homeworks where you compute the PCA of faces, images of faces, right? In that case, we were assuming that in the feature space of all the pixels, so if your camera has p pixels, then that would be your feature space of p pixels, right? That space can represent every possible image you could ever possibly take with that camera, right? Not only of every possible image, but every possible image object, excuse me, not every possible object, but every possible object, every possible orientation, at every possible illumination, and even random noise, right? Any image is represented in that space. So obviously we said the subspace that represents only faces has to be a small subspace within that huge space here, right? True, but why does it have to be linear, right? Most likely it's going to be nonlinear, right? So consider that case. Consider I take an object. Let's see. No, how about if I just take, as always, one of these guys. So consider you have this object, right? And I put it right here on the surface. I place my camera right here, and just one illumination source right here, okay? And now I take a picture. And now that point is going to, that image is going to be a point, right, a vector in that space, right? Now what I'm going to do without moving the object or the camera, I'm going to move the light source, right? And I'm going to go in a circle, S1, around the object, right? I'm going to move, say, 1 degree, take another image. Another degree, take another image. What would happen if I did this? Let's think about this for a second. So I'm in my feature space of RP, p pixels in the image, right? And I take a first picture of my object. Remember, I have an object here of some kind. I have a camera that's taking pictures. And now I have a light source, right, that goes in a circle, right, around the object. Okay? Perfect circle. Can define as 1. So the first image is going to be here. Then I move 1 degree. I'm going to take another image. And now that image is going to be very similar to this one, right? Because I've only moved my light source by 1 degree. And it's almost going to be identical to the other one, which in pixel space, right, in that feature space of pixels, means that these two vectors are going to be very close to one another, right? And now we move another degree, and maybe it's going to go here, or even closer here, and so on, right? And over time, this is going to define a function. But that function, at some point, has to get back to the original position because this is going in a circle. So this is a one-dimensional manifold, right? That's what I want. I want to find a manifold. Now, consider that after I have done this circle, I move the light source a little up or down, right? And I do another circle, right? Then what I'm going to see, this is going to move here. Then I'm going to get maybe something like this. And all of a sudden, I have a 2-dimensional manifold, like this, right? And now I want to recover this 2-dimensional manifold, and so on. Okay? So what I want, really, is to find a representation in RQ, Q dimensions, of the dimensions of that manifold, right? So 1-dimensional manifold, 2-dimensional manifold, 3-dimensional manifold, depending how many different dimensions I need to add to my system. Right? Now, of course, in general, I don't know what Q is, right? It's like the same in PCA. We need to find out what Q is. All right. Oops. So what are we going to do? What we're going to do is we're going to use graphical models. We're going to use a graph. Remember graphs that we just talked about a few lectures back? So what I'm going to do, I'm going to take each of these samples that I have is going to be a node of my graph. Okay? And the edges between the nodes is going to be the distance between the distance in that feature space between these sample feature vectors. Okay? So let's see how we can do that. So obviously, this is going to be a weighted graph. Right? Remember? Because I have weights in the edges between the nodes, right? This is going to be a weighted graph with n nodes. And remember, it's the number of samples that I have right here, right? So that's the same number of nodes. These nodes represent each xi, obviously, 1 through n, I1 through n. And now we're going to define the Vij's, right? This is the vertex, right? The vertices that I need to define between node I and node j, as we had before. And this is going to be equal to, let's see, I'm going to have Wij if the distance between xi and xj is smaller than some value. Let's call it epsilon. Okay? And this is to me, this is just a hyperparameter, right? A hyperparameter that I need to either specify or optimize. And I'm going to consider 0 otherwise. What that means is that if 2 points, right, 2 samples, this one and this one, are farther apart, are really far away, right, that distance is larger than some epsilon, then I'm just going to assume they are too far away. So I'm going to equal it to 0, right? Meaning there is no edge in my graph. Okay. And for things that are close by, samples that are close by, I'm going to have an edge. Right? And that edge is going to have a weight which is proportional to that distance. Another thing that you could consider in order to add edges is to consider the k nearest neighbors, right? So for example, you could add an edge if there is a k nearest neighbor between xi and xj, right? So find the k nearest neighbors of xi, the k nearest neighbors of xj, and if there is something in common, then you put an edge, right? And if not, you don't. So you can see that you can start using all these methods and techniques that you now know to define these different terms for these graphs, right? Okay. In this method, Laplacian maps, the weights are defined using an exponential function, right? Meaning this is like a Gaussian, right? An exponential function, meaning if things are very close to each other, I want them to have a really tiny weight, right? Or a very important closeness, right? Instead, rather than tiny. A very important relevance for that because they're very close. And if they are far away, I want them to have a really tiny, tiny relevance or weight, right? So one way to do this is with the exponential function that will consider this distance, neighboring points, very important, and at some point, everything just becomes exponentially small. So I'm going to use the exponential of the distance between xi and xj, and I'm going to use the 2 norm here. Obviously, nobody's preventing you from using any other norm. I'm just going to use the 2 norm because this is our most standard norm in the Euclidean space, but that defines the Euclidean space, but you could use some other type of norm, of course, over some parameter t and t, some parameter defined in the real domain. Now, capital W would be the matrix that has all theWij's, and this was called, what was this called? The adjacency matrix. Very good, right? So this is the adjacency matrix of my graph. All right, good. Now that we have defined the graph, let's see what we can do with it. What we're going to do is we're going to compute the diagonal matrix of weights that is given by, let's see, dii, it's going to be equal to the sum over all the j's of wji, okay? And dij is going to be 0 everywhere else if I different than j. How about that? Okay? You see how this works? So it just compute in a diagonal matrix that has all the weights aggregated for that node I, right? That node I has many edges. It has an edge, in fact, to every other possible node in the graph, right? But many of them, majority of them are 0, but some of them are not, and it just aggregate them. Okay? And now from this, I'm going to compute the Laplacian matrix. That is given by L. L is the Laplacian matrix, is equal to D minus W, the adjacency matrix. Okay. Okay. What is that Laplacian matrix? Now, this Laplacian matrix L, what it really measures is the number of spanning trees. Remember the concept of trees within a graph? It actually computes the number of spanning trees that we have in the graph. And in general, the Laplacian matrix computes the degree of the node Vi. In our case, Vi, remember, is xi, right? Our samples. Such that, let me do that Lii, right? The elements of the diagonal of that Laplacian is equal to the degree of Vi, okay? And Lij in general, okay, I don't know what I call this, small l. Lij in general is going to be equal to -1 if I is different than j and Vi is adjacent to Vj, and Lij is going to be equal to 0 elsewhere. So I don't want to spend too much time on this, but let's probably see a very straightforward, very simple example. So I'm going to do a very small graph that will hopefully illustrate this clearly. So imagine that I have this undirected graph here. Okay? This is a possible undirected graph. And let's see what the Laplacian matrix will look like according to these derivations that we have given here and these definitions. So in the diagonal, let's start in the diagonal. The diagonal elements are going to compute the degree of my node, right? Okay. Degree and series is not the same thing. My phone thought that I was talking to it. Okay. So the diagonal computes the degree of the node, right? So for the node 1, should be the node. For the node 1, how many edges do I have? 2. Very good. Excellent. How about for the node 2? 3. Very good. How about 3? Still 3, right? How about for the node 4? 3, and so on, right? You see how this goes? Now, we said that Lij is going to be -1 if I is different than j and Vj is adjacent to V, or Ni is adjacent to Nj. In this case, 1 is adjacent to 2, so that's going to be -1. This is going to be -1 as well because this is an undirected graph, right? But how about 1 and 3? Are they adjacent? No, so 0, right? How about 2 and 3? Are they adjacent? Yes, so -1. and so on. You see how this works? Right? So that's the type of Laplacian that you are going to get. Now, because we have undirected graphs, these matrices, right, the Laplacian is symmetric. Okay? So Laplacian is always going to be symmetric and positive definite in our case. Okay? It also is true that the number of connected components in the graph is the dimensionality of the null space of the Laplacian matrix. Okay? So you can consider the Laplacian matrix as a function, right? It's a functional mapping that goes from our vertices to a number, right? A real number. Right? Nothing else than a functional mapping as everything else that we do here. Okay, so now let's see why I introduced this new matrix, the Laplacian matrix, right? We want to see why we have this matrix, why we have to find this matrix, and how can we use it to solve our problem. So remember, what we're going to do is map, right? So we want to do mapping of our data using the Laplacian. That's what we want to see how we can do. Our goal is to find the mapping from p dimensions to q dimensions, right? Oops. So I'm going to consider the similarity or the distance between yi and yj that are defined, remember, in the q-dimensional space, right? Now, the distance between yi and yj has to be similar to which other distance? Xi and xj, right? That's what I want. Excellent. So what I'm going to do is I'm going to write yi minus yj square, right, times what is defining the similarity of xi and xj? My weights, right? My weights are going to be 0, right, if these are far away, right, in which case the distance between yi and yj I couldn't care less, right, because it's too far. It doesn't matter to me. But the closer they are, the more relevance I want, the higher the weight, and the more relevance I want to give it, right? So if I multiply that distance between yi and yj, that's exactly what I'm doing, right? And now I want to sum over for every ij pair that I have, right? And what do I want? I want to minimize this criterion, right? This objective, that I want to minimize this. I'm going to say that I'm going to minimize 1 over 2 this criterion for mathematical convenience here. And I want to find the arguments, right, that gives me that solution. Now, let me rewrite this equation in matrix form, as we always do. This is the same as the argument that minimizes y transpose Ly, where L, or this is L, because, let's see this. Let me do this. Let's do this. This is the same as the sum over I and j of yi minus yj squared, right? Times wij, which is equal to, let's see, if I actually do the computations here, right? This is equal to, let's see, the sum over ij of yi squared plus yj squared minus 2 times yj, right? Is that right? And all these times wij, yes? Okay, and this is the same as, I'm going to write yi square, this first term, oops, sorry, I forgot the summing term, right? yi square times these weights, right, that are given for yi as the diagonal matrix that I have, dii, correct? And plus the sum of my, what do I have? Yi, so now yj square djj, right? Same thing for the second one. Minus 2 times the sum of yi yj times wij. Okay? Now, this equation that I have here, does it look familiar? dii, dij, and wij is nothing else than this equation, right? And therefore, I substitute this by this equation, this matrix, times y on each side, right? And that gives me the equation that I want to minimize, which is given by the Laplacian, okay? You see that? So that's the matrix I actually want to use in my criterion. And of course, this vector, right? Y is equal to y1 through yn. Okay, that's my vector. Okay, any questions thus far? No? All right, I have like 3-4 more steps to do that. I'm going to do this in our next lecture, but go home and look at this and think about how am I going to solve this? Does this equation look familiar to you? It should look familiar to you, right? You want to minimize this equation. Have we seen that equation before? Which algorithm? PCA, very good, right? PCA. So the amazing thing about this algorithm is that it shows that you can find a nonlinear manifold using linear methods. That's what's surprising about this, right? That you can actually solve for a nonlinear function even though you're using linear methods. All right, I'll finish this up, I'll wrap this up in our next lecture, and then we'll go back to classifiers, all right? I'll see you then.